Good morning and welcome to today's ETSI webinar. My name is Ultan Mulligan. I'm Director of Communications at ETSI and I'm your moderator today. Our webinar today introduces us to ETSI's software reconfiguration framework for mobile devices. ETSI has been working for a number of years on software-defined radio, reconfigurable radio systems and cognitive radio in our technical committee ORS, reconfigurable radio systems, and we have some results to show for that. Today's webinar will outline key differences between the ETSI software reconfiguration framework and the well-known software communications architecture, or SCA. It'll detail our overall architecture, including the concept of the radio virtual machine. Finally, but very interestingly, we'll comment on the regulatory framework in Europe around software reconfigurable radio systems. Our presenters today are the chairman of ETSI's Technical Committee on Reconfigurable Radio Systems, Dr. Markus Möck of Intel. We'll also have Dr. Seungwon Choi, professor of Hanyang University in Seoul, and Dr. Vladimir Ivanov of LG Electronics. And obviously, all three of them are active participants and contributors in our TC-RRS. Now, before I hand over to Markus, I'd like to remind you just of some quick points about our webinar today. A recording of our webinar will be available on demand immediately after the end of this webinar, or within about 5 minutes. You can find that recording at exactly the same location as you found this live webinar, on the ETSI website or on the Bright Talk channel. I encourage you to ask questions at any time. You just click on the Ask a Question button. You have to write your questions. We'll take your questions at the end of the webinar. Now, if we don't get a chance to answer your question, we'll try and get back to you after the webinar, so don't worry. Please, I encourage you to share the webinar using the social media buttons above the viewer. Please feel free to use the full screen feature and increase the slide or the screen size into full high definition. You'll find the button on the bottom right-hand corner of your viewer. That may be useful for some of the charts and diagrams which we have to show. You can also view the slides in PDF form. They're already available as an attachment from the Attachments button. And please don't forget to rate this webinar and give us some feedback using the Rate This button. Now, I'll hand over to you, Markus.
Thank you very much, Ultan, and welcome everybody. I would like to welcome you to this webinar on software reconfiguration and related standards that are currently being developed by ETSI. Let's just start with a quick overview. So what we are going to do in this webinar is to take a look at software configuration from different angles. We first start from the technical angle and then go into regulation and security matters. And it is clear that we will also focus on some key innovations introduced by ETSI, and this in particular includes the radio virtual machine. We will understand in this webinar how our concept fundamentally differs from past SDR and software reconfiguration approaches, and thus will make this new approach really viable, in particular for commercial mobile device applications. So let's go first into the motivation and objectives. So the basic objective of the ETSI work is to define a software reconfiguration ecosystem. And this is done in particular with a focus on mobile devices. And we are tackling this objective from 3 angles. The first angle is the technical angle, and in our technical committee, TC-RRS, we have been defining architecture and interfaces. And we will see during this webinar that the interface definition is still ongoing in some domains, and there is still the opportunity to participate. Security features have been considered based on specific identified threats, and we will learn at the end of the webinar which specific solutions we are going to propose in order to ensure end-to-end security. Then finally, we take a look at regulation matters. It is obvious that software configuration that affect radio characteristics of a mobile device need to be handled appropriately in declaration of conformity in particular, and we have been developing solutions in close collaborations with regulation administrations in order to exactly address this problem. So now let's move forward and have a look at the real difference of our approach with respect to past efforts related to software-defined radio and in particular the software communications architecture, which is very known in particular in the military field. So I would really like to emphasize that the ETSI approach is fundamentally different from this past effort for a number of reasons. In particular, the past effort on SDR has considered software reconfiguration rather from a computer architecture perspective. So we have been assuming that a high computational power platform is able to take reconfiguration code in order to execute a full new waveform or a full new radio access technology. This has been proven to be difficult for commercial applications. So what we are doing differently here is that we are starting to look at the problem from a different angle. So instead of starting to look at this problem from the computation architecture perspective, we are rather taking a look at it from the software reconfiguration perspective that is already existing. And this is in particular software applications for smartphone platforms. So what we are doing is simply to go from existing software applications that you can buy in the well-known stores, and we extend the corresponding features such that radio parameters can be altered. So we really attack the problem from the other end, and we believe that this is going to be much more promising for commercial applications. But we will see in detail in the sequel how this is going to implement it in practice. So with that, I suggest that we start going into the technical details, and I would like to hand over to my colleague Vladimir Ivanov from LG Electronics. Please, Vladimir.
Hello, everybody. The first mention of radio virtual machine, let's call it as RVM, was made by Vudaitis and Mitala during SDR forum workshop in 2000. In this approach, radio access technology I implemented as software for RVM. Such software we will call as radio applications. So RVM plays key role in presented technology. We start from the term reconfigurability. Two types of reconfigurability are considered. The first one is parametric reconfigurability. In this case, we can change only parameters of algorithm from radio applications. The second type, structural reconfigurability, which assumes that algorithm components mapping on hardware can be changed. It means, in principle, we are going to allow that, for example, fast Fourier transformation can be executed by different processing elements in our hardware platform. Another possible case when algorithm components can be changed. We are able to replace some components by more advanced ones developed by third party. Nowadays, industry supports only parametric reconfigurability. Therefore, radio application is one monolithic component which structure is hidden. The proposed technology is going to step further when vendors can make decisions and open some internal components or even whole radio application for updating or replacing by third party. This technology also proposes the way for adding new, more advanced radio access technology running on existing hardware platform. Control of reconfigurability is carried out by runtime environment and RVM. As I described on previous slide, reconfigurability assumes that radio application is not a monolithic component, but rather an assemble of components with some structure. Let's take a look at the fragment of Wi-Fi receiver on the left diagram. This fragment includes quite typical signal processing functions, such as fast Fourier transformation, equalizer, etc. Therefore, it makes sense to put such functions in some library, which we will call a radio library. These functions can be used for the presentation, of course, not only Wi-Fi receiver. But is this enough for algorithm specification? No. Algorithm assumes some behavior and conditions when algorithm function will be triggered. So now I am going to add such type of conditions. We will insert data object between functions. These objects can be full or empty. Functions are triggered if all input data are full. And here, triggering means that functions read all input data and make them empty. And after that, to process input data, and write down result into output data if they are empty. That's it. And it's enough to have mathematically strong model for the presentation of any algorithm. Let me summarize briefly. We represented algorithm as data flow graphs consisting of data and functions which we will call operators. Operators are taken from a radio library. Operators are data-driven. It means that they are triggered by full data. Operators are executed concurrently and asynchronously. Operators might be complex and include other operators and data. After having such model, we are ready for RVM description. RVM is a very simple parallel computer. It's actually some abstraction of parallel computer. It has data path control unit, program and data memory as usual CPU. What is the difference? First of all, we have not one but multiple data allocated in infinite flat data memory. Then, instead of one LU, arithmetic logical unit, we have multiple and more generic abstract processing elements, APEs, which are capable of executing not only arithmetic and logical operation, but all operators from radio library. In this way, we consider arithmetic and logic operation as a part of radio library and a particular case of operator. APEs work concurrently and asynchronously. They are data-driven and triggered by full data. APEs and data are bound by abstract switch fabric, ASF. It's clear, if you put number for data, abstract processing elements, and switch fabric ports, we will be able to specify particular data path configuration by incidence matrices. We can binary encode these matrices. These are exactly configuration codes which define data path configuration. These config codes are stored in program memory and are fetched by control unit. So in RVM, we have just only one instruction, configuration. This instruction consists of three components: configuration data, APEs, and ASF. Configuration data lies in memory allocation for data and initialization some data. Configuration APEs is expressed in downloading radio library functions collected in basic operations block. And the configuration ASF describes particular binding data and abstract processing elements. Config code execution is started immediately after data path configuration, and config code execution is stopped when there are no more full input data in data path. The result of computations is full output data. As you can see, we don't need to any additional control or sync up signals for execution. It makes control unit quite simple and very efficient in terms of control overhead. Okay, next slide. We divided that compilation phase config code to produce config code in two phases. The first one is front-end compilation, shown on this file. Radio application is presented as source code. We don't put any constraints on programming language for source code. So radio application can be written in C, C++, or whatever else. But source code should be past parallelization, and as a result, it should be represented as data flow graph, which we discussed earlier. This graph is input for RVM compiler, where the graph is mapped on scalable radio virtual machine. The result of this compilation phase is config code for RVM, which is totally independent on hardware platforms. This code can be stored in a radio application store, and it can be used by vendors for mapping on particular vendor's platform. This process is carried out during backend compilation phase, which we will observe on the next file. There are two options for backend compilation. The first one is do not do compile at all, and the second one is to compile eventually. The first option means that the vendor selects a variant of native RVM implementation embedded in vendor's runtime environment. In such case, radio application config code will be interpreted by the implemented RVM directly. The second option means that config code is compiled by vendor's backend compiler. There are two variants for compilation. It might be JIT, just-in-time compilation, when executable code is generated during runtime, or it might be AOT, ahead of time compilation, when executable code is created before runtime. In both cases, executable codes are embedded in vendor's runtime environment, which controls radio application execution on vendor's platforms. Runtime environment is located on the top of radio operating system and radio control framework, RCF. These elements of reconfigurable architecture will be explained by Professor Choi. As a short conclusion, the proposed RVM-based approach ensures config code portability. We don't put any limitations on source code or how to map source code on particular platform. Backend compiler is vendor's tool. Vendors don't need to open details of hardware implementation. They can select the most effective way for creation high-performance radio application. So, Professor Choi, we can start.
Thank you, Vladimir. Thank you, everybody, for joining us today in this webinar. I'll be introducing the architecture and interfaces, architecture of the reconfigurable mobile device and interfaces related to that architecture that we are suggesting. Okay, let's get started. Okay, in this slide, I'm introducing the architecture component for the radio reconfiguration. First of all, the reconfigurable mobile device is denoted as a radio computer, as you see at the bottom of the figure. In other words, we want to see the reconfigurable mobile device as a computer that executes the downloaded radio application code. At the bottom of the figure, we have a radio platform which includes baseband processors and RF transceiver. The baseband processors might consist of programmable processors and or dedicated hardware accelerators, and the RF transceiver might consist of frequency up-down converters, AD/DA converters, and antennas. On top of the radio platform, we have unified radio application on your right-hand side, which include software radio application code downloaded from outside the radio computer. Once the radio application code is downloaded onto the mobile device, it is nothing but a software to be executed on a mobile device, which we call radio computer. So no matter whether the downloaded radio application code is LTE, WCDMA, Wi-Fi, or whatsoever. It is just a software to be executed on the radio computer. So that's why we decided to call it Unified Radio Application. So once the radio application code is downloaded onto the radio computer, it is denoted as URA, Unified Radio Application. So at the left-hand side of the URA, we have Radio Control Framework, which is a part of real-time OS. In order for the radio computer to be reconfigurable, we need some extra functionalities in addition to the functionalities provided by ordinary RTOS. So 5 software entities shown inside the radio control framework, in this figure, are those other software entities to provide those extra functionalities required for the radio computer to be reconfigurable. For example, Configuration Manager, which is shown at the left-hand side of, inside the radio control framework, executes activating or deactivating desired or undesired radio application code. Similarly, Radio Connection Manager, which is drawn just right-hand side of the Configuration Manager, is a software entity to provide the functionality of installing or uninstalling radio application code. So similarly, we need some extra functionalities for the for the radio computer to be reconfigurable. Okay. So on top of radio control framework, we have communication services layer on top, which includes 4 software entities. Each of these 4 software entities is to generate a command to activate the corresponding functionality of the radio control framework. For example, administrator shown at most left-hand side inside the communication services layer generate a command for the configuration manager in the radio control framework to activate or deactivate the desired or undesired radio application code. Okay? So consequently, the standard architecture shown in this slide of the mobile device specifies what extra functionalities are required for the mobile device to be reconfigurable. Okay, let's go to the next slide. Okay, in this slide, I'm introducing interfaces with which the different layers can interact with each other in the standard architecture introduced in the previous slide. So first of all, multi-radio interface, that is denoted as MURI in red color, are the set of interfaces between communication services layer and radio control framework. Similarly, Unified Radio Application Interface, that is denoted as URI in blue color, are the set of interfaces between radio control framework and Unified Radio Application. And finally, reconfigurable RF interface, that is RRFI in orange color, are the interfaces between Unified Radio Application and RF transceiver. So besides these 3 kinds of interfaces, we define another kind of interface, namely radio programming interface, which is shown on your left-hand side of this figure, and that will be explained in a little more detail at the next slide. So by the way, we have completed the defining MURI, URI, and RRFI interfaces, and we are now making RPI. Okay? So let's go to the next slide. Okay. Radio programming interface are a set of interfaces that interface between radio application programmer and the reconfigurable mobile device. So it is exactly like, API, application programming interface, in an ordinary computer. So radio programming interface consists of many standard functional blocks. For example, fast Fourier transform, interleaver, bit-to-bit decoder, turbo decoder, correlator, adder, subtractor, etc. The normative description of all these standard functional blocks are provided in a software entity, which we call radio library, that Vladimir kindly explained previously. Referring to the normative description of all the standard functional blocks contained in the radio library shown at the left-hand side of this figure. Radio application programmer generates the radio application code. Okay? The software provider will take a look at what standard functional blocks are available and what are those the normative description of each standard functional blocks. Knowing that, they make LTE code, Wi-Fi code, and so on. So assuming the radio application code is provided in the form of intermediate representation, the radio application code will be first front-end compiled, and the result of front-end compilation of the radio application code is denoted as config codes as shown in this figure. And config codes are uploaded at the public domain, which we call Radio App Store, and downloaded into your mobile device. If it is provided in the form of intermediate representation, then it will have to be back-end compiled at your mobile device. For the efficient back-end compilation, we suggest the idea of radio virtual machine, which was explained kindly by Vladimir in this webinar. Okay, let's move over to the next slide. So in this slide, we introduce an architecture reference model for multi-radio applications. At the center of this figure, you can see many radio application codes, downloaded. RA1, RA2, RA3, up to RAN. So we have downloaded N different radio application code in this example. As I said previously, once it is downloaded onto your mobile device, it is denoted as unified radio application, and I already explained why. With the functionalities provided by the radio control framework that I just explained in the first slide, desired radio application code will be executed on real-time OS, which is denoted as radio OS in this figure. Okay, let's move forward to the next slide. So finally, this slide tells you how the radio application code is provided from radio application programmer to the final destination, that is your mobile device, via Radio App Store. So assuming the radio application code is provided in the form of intermediate representation, the radio application code is first front-end compiled during the design time, as shown in this figure on your left-hand side. Then, together with the radio controller code, which is needed to process the context information of the given radio application code, radio application package is formed, and radio application package is uploaded onto the Radio App Store. And during the installation time, the radio application code is downloaded from the Radio App Store into the target mobile device. And if it's provided in the form of intermediate representation, which was called config codes, as explained by Vladimir, it will have to be back-end compiled during the installation time. So finally, during the runtime, the executable code provided by the back-end compiler is executed as shown in the figure on your right-hand side. So this is the end of my presentation about the architecture and interfaces. So I would like to move the presentation to Marcus. Marcus?
Thank you very much for the detailed explanation of our architecture and the RVM. So now we are going to take a look at related regulation and declaration of conformity challenges and solutions. So before going into the specific solutions, a key question to be looked at relates to the responsibility. In the context of third-party software reconfiguration, we have, of course, several stakeholders which need to be taken into account. In particular, we have the original equipment manufacturer, as you see on the upper left-hand side, and the software manufacturer on the right-hand side. We have been discussing in the TCRRS committee together with regulation administrations on how to handle a responsibility in such a context. In this discussion, we came to the conclusion that it is unfeasible in practice to split responsibility really between hard hardware and software manufacturers, because in the end it will not be possible to clearly identify whether a misbehavior of a device originates from erroneous hardware design or erroneous software code. So that is why we have chosen to go for a single conformity contact entity model, which basically means that we need to introduce a single entity, as you see in the middle of the left-hand side of the figure, that is taking full responsibility on the joint operation of software and hardware. And as we are going to see, this is exactly matching with the latest regulations that are given by the Radio Equipment Directive in the European Single Market Framework. So it basically means when a device is not behaving correctly and, for example, creating interference to other equipment, the National Regulation Authority may have a single contact point, the conformity contact entity, to interact with and to identify suitable next steps. And here, it is very important to understand the role of the RVM actually, because the RVM provides a secure and contained execution environment that is fully separated from the rest of the other underlying modem hardware. So it allows basically the hardware manufacturer to open up specific underlying hardware features in a controlled and gradual way. And this is very important for this responsibility chain, because the hardware manufacturer may, for example, start to open up only very specific underlying hardware features for software manufacturers, and thus actually the overall responsibility can be controlled. To give a specific example, the hardware manufacturer may start with giving access to antenna selection features only. So a software manufacturer can, for example, implement a software component that optimizes antenna selection. If something goes wrong, the conformity entity is contacted, and since the openness of the platform is controlled, the responsibility to be controlled by the conformity entity can then be clearly identified, and the conformity entity can clearly see whether the bug is rather on the software manufacturer or the hardware manufacturer side. So it's really important to understand that we have here a different approach compared to previous SDR technology, where typically the entire platform is opened. So the difference is really that we are working with a secure and contained environment that is given by the RVM. So let's just have a look at the current European regulation framework. So you may know that the European Commission has issued recently the so-called Radio Equipment Directive, which replaces the previous RNTTE directive. And it will be the only directive to be applied for putting equipment into the single European market from June 2017 on. So here we have two key articles, so it's Article 3.3i and Article 4, that relate to software reconfiguration, and these are new articles. They have not been present in the RNTTE directive. And the software can actually only be loaded into the equipment when the compliance of the combination of software and hardware is demonstrated. This is given by Article 3.3i, and Article 4 then deals with the usage and the execution of the corresponding software component. So the message is basically that the policymakers really want to make this technology happen and provide specific support to have it implemented. So how to deal with certification and regulation aspects? A key problem is actually that whenever radio parameters are modified through software, we need to update the declaration of conformity. And the question is how to do this. in the past, we have been typically issuing a piece of paper saying that a certain equipment is in compliance with the essential requirements of the directive. And this is, of course, no longer possible if post-sale reconfiguration through software takes place. So for this, we believe that Annex 7 of the Radio Equipment Directive provides a solution. It relates to simplified declaration of conformity. It basically allows that the device is no longer issued together with a piece of paper, but just with a pointer pointing to an internet address where the actual declaration of conformity is located. And it is thus possible to update this declaration of conformity again and again by adding those software components that are being authorized by the responsible entity. So basically, once this address is updated and the corresponding responsibility is then again taken by this overall responsibility contact entity, as we have seen before, then only the software components can be made accessible to users and can only then be loaded into the equipment and finally be used. And with that, we believe that we have a regulation and declaration of conformity environment that allows to bring the corresponding technology to the market. Now let's finally have a look at security. So it is actually of key importance, of course, that the responsibility contact entity is certain that end-to-end security is guaranteed and that only authorized radio application packages can finally be provided to a device which are in compliance to the list of devices that are given by the applicable declaration of conformity. And so end-to-end security needs to be provided. And how can this be achieved? So we have identified in this context several steps. So the first one relates to communication security, which provides confidentiality, integrity, and authentication of parties between the radio application store and the reconfigurable equipment. Then in the next step, we guarantee integrity and proof of origin for radio application packages in the declaration of conformity, and this is typically done using digital signatures coupled with an identity management framework. The third step relates to non-repudiation, which allows traceability of assets and accountability. And since RRS standardizes a way to reconfigure devices, it is really important to have a clear view on the inventory that can be proven at all times, and this is feasible with our approach. Then finally, we believe that the binding of the declaration of conformity to a specific reconfigured equipment is important in order to mitigate counterfeit as well as attempts from users to install rogue radio applications. Now let's have a look at an example. How does this work in practice? So at the first time, the radio application store and the reconfigured equipment must authenticate at the level of the communication layer. After a protocol exchange, it is determined that a radio application must be downloaded. However, before this can be done, a new declaration of conformity needs to be made available and to be downloaded. The reconfigured equipment actually verifies the integrity of the declaration of conformity and that it originates from the correct conformity contact entity. Then, in the third step, the radio application package is downloaded. Its integrity and origins are also identified. And finally, before installing the radio application, the reconfigured equipment verifies that it is covered by the available declaration of conformity. This is how we ensure that the reconfigured device will definitely comply to the radio equipment directive. So this is obviously just a quick overview on the most elementary security features please let me invite you to take a look at the specific RRS security model webinar, which is scheduled for the 1st of June. Now let me conclude and give some outlook on where the technology is going to head in the future. So first of all, it is important to understand that ETSI TC-RRS has defined a series of European standards. You see actually in the table below in green color the standards that have already been issued. The interfaces are actually contained in a multi-part deliverable with 4 parts, all of those consisting to one of the interfaces that have been identified by Professor Choi previously. And documents 1 and 2 relating to the multi-radio interface and the reconfigurable radio frequency interface have already been issued. The standard related to the unified radio application interface is currently in the final approval stage. And you currently have the possibility to contribute to the 4th deliverable relating to radio programming interface, or RPI, which is still underway. And what we are also doing is to further update our requirements and architecture deliverables with the latest findings we have from the security studies. So then, to give just a final outlook, we have been focusing on the mobile device so far, but we believe that this technology may also make sense in the infrastructure, and in particular, it may be a perfect complement to an available network function virtualization framework. So we believe that in network function virtualization, actually it may make sense to allow the available hardware resources to also alter radio parameters, which is currently not the case in the existing technology. So that's it from my side, and I hand back to Ultan for questions and Q&A.
Thank you very much, Marcus, and to all of our speakers today. Okay, now it's time for your questions to our speakers. If you're watching this live, there's an Ask a Question button just above your viewer. If you've been watching it in full screen mode, you need to exit full screen and enter your question. So please start writing your questions and we'll deal with them. As I said in the beginning, if we don't get a chance to answer your question here on the live webinar, then please ask it anyway and we'll try and get back to you. If you're watching this in the recorded version, please send your question to info@etsi.org, info@etsi.org, and we'll try and route it accordingly. And also, please don't forget to give us a rating on this webinar. It's very useful feedback. If you've got any comments, positive or negative, we'd love to hear them. And don't forget to download the PDF version of the slide. Okay, I see we've actually 1 or 2, in fact 3 questions here at the moment already. First one is maybe quite a fundamental one. We've talked about software-defined radio and reconfigurable radio. What is the difference, or is there a difference? Marcus, who should handle that?
Yeah, I believe Vladimir is probably in the best position to take that question.
Okay, thank you for this question. It's actually a really fundamental question. And SDR originally supports traditional von Neumann computational model. And it's actually is not very efficient. It's not efficient at all, let me say, when we consider complex heterogeneous hardware platform like what actually vendors proposed for mobile phones and so on. So just to make it efficient, this approach efficient, we actually replaced von Neumann computational model by more efficient by concurrent model actually. This is the first. The second, this model actually behave in the same way as any native hardware platform. So we don't need any overhead to translate from one behavior to another behavior. This is the first part of my answer. The second part of my answer that usually also SDR is identified by SCA architecture proposed by GTRS. So it's a bit another point of view, but nevertheless, SCA software communication architecture, it's actually try to separate radio application from hardware by providing corresponding API. But it means that if you will put some API between software and hardware, it means we will put some constraints on hardware. And from one side, this is very complicated software development because hardware is very complex with different behavior. From another side, artificially introduce some constraints on hardware. So it's not a good way, and this is the point where SDR actually lost efficiency. That's why we proposed our approach. And the last point that reconfigurable radio assumes that we can consider as software any hardware with any level of flexibility, starting from ASIC and finishing with hardware considering as some CPU or DSP or whatever else. So this model actually covers all possible variants from ASIC up to CPU. This is my answer.
Okay. Thank you very much, Vladimir, for this. Maybe I just add that a key aspect in our solution is also that the responsible entity is able to control the openness of the platform and can actually add additional access to underlying radio parameters in a gradual and stepwise way. And this is very important that we do not need to grant access to the entire platform, but we can control the openness, which makes it really much more attractive to industrial players. So please, Ultan.
Okay. Yeah. No, thank you. That's quite comprehensive. I have a question now which somebody has entered, which I think is probably more for you, Marcus, because you covered the regulatory aspects at the end. What's the latest status or news from Europe on regulations for software reconfigurable radio? They've heard something about a new committee. Maybe, are you following that in detail, Marcus? You've commented on that already.
Yes. Actually, it is important to understand that the European Commission is using the so-called Telecommunications Conformity Assessment and Market Surveillance Committee, or TCAM, which takes an advisory role. And in this committee, any matters regarding conformity assessment and market surveillance is considered. And this committee just happened to create an SDR subgroup, which is going to meet for the first time on the 24th of June, 2016. And in this context, actually, the next steps on dealing with the Articles 3.3i and 4 in the Radio Equipment Directive related to software reconfiguration will be handled. And we expect some new directions from the political side related to this topic.
Okay, thank you. I have one last question at the moment, unless somebody starts writing a question quite quickly, and it's about the current status of work inside ETSI's RRS committee. So what are you currently working on in the RRS committee? What are the key topics you're working on?
Yeah. So thank you, Ultan, for this question. Yeah. So basically, we are currently finalizing the last deliverable of this 4-part interface activity. And this relates in particular to the radio programming interface. and you will be able to contribute to our next meeting, in particular on the topics on load, linking, and initialization of the platform. You may be able to contribute to the topic of compiling for the radio virtual machine and actually related specifications. So it's quite on a detailed level, but there is definitely the opportunity to contribute and shape the standard we are currently working on.
Just as a reminder, it's not part of the question, but the next meeting of this committee RRS is coming up where and when?
So the next meeting is going to happen on the 31st of May to 3rd of June in San Diego, California, US.
Okay, and that meeting is open to all ETSI members, isn't it?
This meeting is open to all ETSI members, indeed.
Okay. So if you're interested, it's an open call to participating. Okay, I think that's all the questions we have at the moment, but as I said, if you're watching this on the recorded version, you can address your question to info@etsi.org. Just please identify the webinar precisely so that we can route your question correctly. Please don't forget that the next webinar on this topic is coming up on the 1st of June. It will be in European afternoon, 4 p.m. at European time, and it's focusing on the security model, which Marcus has briefly covered, but we'll be going into more depth on that. You'll find, I think if you're watching this on the Bright Talk webpage, you'll find a link to register on immediately to the right of the slides, because that's the next upcoming webinar. You'll find it in our list of events on the ETSI website, etsi.org/news and events. You'll find it, or even on the homepage, you'll find it directly. And so I encourage you to register for that one. And likewise, if you have questions which go a little bit beyond the security model but are still focused on reconfigurable radio in general, you can still post them at that webinar. So I think that's basically all we have. I'd just like to say thank you to our three presenters today for taking the time in their busy schedules to present this webinar, to actually prepare such detailed content. And I encourage you to share the webinar. I encourage you to review it again, to share the links to the recorded version, and to download the slides and go through this in detail. And of course, to get involved in our committee RRS, if that's what interests you. Any final words, Marcus?
Yes, I would also like to thank you, Ultan, for making this possible, and of course, thank you very much, Vladimir and Seungwon, for participating to this. It's always a pleasure working with you. Thank you.
And of course, thank you to our audience, which is the most important part of it. Okay, with that, we'll say goodbye to you, and thank you very much for listening in. Bye-bye.
Thank you. Bye-bye.